Hello there, welcome back to Differential Equations by Alexander. Alright, so today we're going to talk about the Cauchy-Euler equation, and then we're going to give examples today. So examples. But before we do that, I just want to remind you what we did in the previous video. So we looked at the homogeneous equation, which was this guy with a 0 at the end, and then this is the Cauchy-Euler homogeneous equation. And then we said that in order to solve this, we have to look at the auxiliary equation. And so the auxiliary equation turned out to be this guy in blue. And so now the question becomes, what is the value for m? And then we said in the previous video that we have three different cases. We're going to use the quadratic formula for this, and then we are going to get three cases. So the first case is whenever the quadratic formula gives you two numbers, so m1 and m2. And in that case, your two linearly independent solutions are going to be x to the first number m1 and x to the second number m2. All right, so those are your two linearly independent solutions to your homogeneous equation. So that's case number one, where the quadratic equation formula gives you two different numbers. Now, the second case is whenever the quadratic formula only gives you one number, so basically it's repeated. So in that case, your first solution, it is going to be x to the power m1, and your second solution is going to be x to the power m1, but you have to multiply by the ln of x function. So that's the extra thing that we have to multiply. And then remember that this is for the Cauchy-Euler equation. This is the homogeneous equation. And now we have one more case where we get from the quadratic formula. So sometimes we get that the m numbers are going to be two complex numbers. It's going to be alpha plus I beta and alpha minus I beta. So, but we have to identify the alpha and the beta. And so these are complex numbers. And in this case, your linearly independent solutions are going to be of this format. It's going to be x raised to the alpha power cosine of beta ln of x. So we have to be careful on the format here. And then the second solution is going to be x to the alpha sine beta of ln of x. And so these are your two linearly independent solutions that are solutions to the homogeneous equation on the very top. All right, so what I want to do, I want to give you examples of the three cases. And then, so case number one will be question number one. And so here, the auxiliary equation will be, again, am squared plus b minus a m plus c is equal to 0. And here we have to be careful that we have to identify the a, the b, and the c. And this is the a, in this specific problem, is going to be a is equal to 1, b is going to be 8, and c is going to be equal to 6 in this specific problem. So the 1, the 8, and the 6. So we are going to use the auxiliary equation, but remember this is the auxiliary equation for the Cauchy-Euler equation. So plug in numbers, and then we'll get m squared plus the 8 minus 1 gives us a 7m, and then plus a 6 is equal to 0. So the first thing that we try to do is, can we factor this? If we are not able to factor, then we use the quadratic formula. But in this case, we can factor, and then the factor is going to be what? M plus 1, and then m plus 6 is equal to 0. So that means that the m is equal to -1 and m is equal to -6. So we got two numbers from either from the quadratic formula or from the factoring. So we have m is equal to -1 and m is equal to -6, our two numbers. And so what that means is that our two linearly independent solutions to the homogeneous equations are going to be y1 is going to be x raised to the first power, which is -1. And then the y2 is going to be x raised to the other power, so which is -6. And so what that means is that the general solution to the homogeneous equation is going to be the combination of the y1 and the y2. So c1 multiplied by x to the -1 plus c2 x to the -6. All right, so this is going to be the general solution to the homogeneous equation, which is on the very top. So it's a homogeneous equation, and it's a specific type of equation. It's the Cauchy-Euler equation. All right, so that's the first example where you have two values for the m coming either from the quadratic formula or from factoring. Now let's go into question number two. Question number two is going to be the case where you have the only one value coming out from the quadratic formula. And so let me just write down the auxiliary equation again. And so remember that it looks like this. So am squared plus b minus a m plus c is equal to 0. the A, B, and C from the given Cauchy-Euler equation. So that means that the A in this case is a 2, the B in this case is a 6, the C in this case is a 2. So we're going to plug that information into the auxiliary equation that we have, and then we'll get the following. We'll get 2m squared plus, and then b minus a gives us 6 minus 2, which is a 4m, plus what a c is equal to the number 2 is equal to 0. In this case, we can factor out the 2 everywhere, or divide by 2 everywhere, and then we're going to get m squared plus 2m plus 1 is equal to 0. And now the question is, can we factor this? If we are not able to factor, we can always rely on the quadratic formula. But if we can factor, we should. So can we factor? In this case, is yes again. So this is going to be m plus 1 multiplied by m plus 1 is equal to 0. So that means that your value for m is going to be m is equal to -1, and then m is equal to -1. I'm repeating this because I want to emphasize that this is the second case where the m value is being repeated twice. So this is the case where we have a repeated root. And so that means that the linearly independent solutions to this homogeneous equation are going to be the following. This is going to be y1 is going to be x raised to the, and then the solution is going to be x to the -1, but then we have to multiply by the ln of x. Okay, so that's the tricky part here. We have to multiply by the ln of x. So those are your two linearly independent solutions. And now we want to write down the general solution for the homogeneous equation. So we have this homogeneous equation, a Cauchy-Euler homogeneous equation. And then so the general solution is going to be the combination of y1 and y2. So c1 multiplied by x to the -1 plus c2 x to the -1 ln of x. All right, so that is your general solution for this question number 2. All right, so that's the second case. And now we have one more case to deal with. And so here, let me go again and write down the auxiliary equation again. So let me just write it out a little bit smaller this time because I will need a little bit more space. So a m squared plus b minus a m plus c is equal to 0. And again, this is the auxiliary equation for the Cauchy-Euler equation. This is only the auxiliary equation for the Cauchy-Euler equation. And again, we have to be careful where we identify the a, which in this case is a 1. The b is a -2. The c is a 3. So now plugging those numbers into the equation, we're going to get m squared. And now b minus a is how much? So -2 minus 1 gives us a -3m. And then the c is a 3. This is equal to 0. All right, so now the first question which we always ask is, can we factor this? And then this is not possible to factor just by looking at it, or at least not so obvious. And so we're going to rely on the quadratic formula. Okay. So, but when you use the quadratic formula, you have to make sure that you are looking at this equation. So forget about the auxiliary equation that you just wrote down in blue, and we're going to use the quadratic formula that we know from high school. And so this is going to be -b, which is this -3, which is going to be a +3 plus or minus square root of b squared, which is a 9 minus 4 times 1 times 3. Divide the whole thing by 2a, which is a 2. So make sure that you are putting the correct numbers because you're looking at this quadratic equation in the black box. All right, so now we need to simplify this. And so this is going to be equal to 3 over 2 plus or minus. And now 4 times 1 times 3 gives us a 12. 9 minus 12, how much is that? That's -3. So this is going to be square root of -3 divided by 2. So now we're going to simplify this a little bit here. So this is going to be 3 divided by 2. And then plus minus I square root of 3 divided by 2. And so what that means is the following. We identified the alpha and the beta. So this is going to be the alpha, and then this is going to be the beta. And so the linearly independent solutions to this homogeneous equation are going to be the following. So this is going to be a little bit more lengthy to write down. So let me see if I can write it down here to the edge. So the y1 solution is going to be x raised to the alpha, which is a 3/2. So 3/2. And then we're going to write down cosine of beta, which is square root of 3 divided by 2. and then we have to multiply by ln of x. So it's a little lengthy. So this is x to the 3/2 cosine of square root of 3 over 2 multiplied by ln of x. Now the second solution is very similar. It's going to be x to the 3/2 again. And now we multiply by sine of square root of 3 over 2 ln of x. All right, so that's y1 and y2. So those functions in gray, those are your linearly independent solutions to the homogeneous equation. And now the question is asking us to find the general solution, and so we need to make the linear combination of the two. So this is going to be y is equal to c1 x to the 3 over 2 cosine of square root of 3 over 2 ln of x, and then plus c2 x to the 3/2 sine of square root of 3 over 2 ln of x. And that is your general solution to this homogeneous Cauchy-Euler equation. All right, so those are the three cases. The last case, the formula gets a little bit more lengthy, but we talked about the three formats, and so now we have given three examples for the three cases. All right, so I hope that this is helpful, and I'll see you in the next time. And next time, we actually are going to solve a Cauchy-Euler equation where we don't actually have a zero here. We actually have a g function, but that's going to be for the next video. All right, so I'll see you next time. Thank you for watching.